this video, I will explain about low-pass filter. Low-pass filter used to eliminate and can be classified into two different types, which are active and passive. Low-pass filtration is based on the components used in the design. If active components such as op-amp and transistors used in the design, while if passive components like resistor, inductor, and capacitor used in the design, and it is known as. For passive low-pass filter, there are three types of circuit. First, RC, RL, and RLC circuit. In this video, I'll only concentrate on the RC low-pass filter. To design low-pass filter circuit, you just need to connect the resistor and capacitor in a series connection. I will show you the connection that I already designed using software. This is my connection: 10 volt, 10 kilo ohm resistor, and 0.01 microfarad capacitor. For this value, resistor and capacitor, you can use any value that you want. V out equals to Xc over Xc plus R times V in. Xc is a reactance of a capacitor, and it can be written 1 over omega C. But the most important equation for low-pass filter is this one. Equation for cut-off frequency is 1 over √2 of its maximum value, and this is the equation for cut-off frequency equals to 1 over 2 pi RC. For this RC, this value of RC, you can use the one that you use in your design. Like my use 10 kilo ohm resistor and 0.01 microfarad capacitor. So I just plug in the value here and I will obtain this answer, 1519.55 Hz. After you get it, go back to the circuit, click PSpice, edit simulation, and wait for a while. Then set up this thing. Click AC swap and then set your frequency, set your range of frequency, and then click OK. After that, click run will appear. Then you click trace, add trace, and then click V out, then click OK. You will. After that, you already know your cutoff frequency. So click this cursor and then find where is the position of your cut 0.59. Okay, cutoff frequency is somewhere here or this one. You can see the value 1.599980 because I cannot get the. So after that, I'll continue my presentation on application of low-pass filter. Application of low-pass filter is used in a transmitter. It is used to block harmonic emission, which might cause interference with other communications. That's all. Thank you.
So I'm going to present about the high-pass filter. Okay, so a brief introduction. The high-pass filter is an electronic filter with the purpose to eliminate low-frequency components. Okay, so it is the exact opposite of the low-pass filter. It has no output voltage up to a specified cut-off frequency at this point. Here in the response curve, this is the cut-off frequency. Up to this point, the frequency up to the cut-off frequency will be filtered out. So the ones that are selected to pass are on the right side of the cut-off frequency. This is the circuit that I will simulate. And for this circuit, I'm using 0.5 mF capacitor, 1 kilo ohm resistor, and 10 volts AC. To find the cut-off frequency of this circuit, we use this equation. Substitute all the values, and this will be the cut-off frequency for the circuit I'm going to use. Okay, so to explain, the reactance of the capacitor is very high at low frequency. So at V in, the reactance of the capacitor will be very high, and the circuit acts like an open circuit, so it blocks any input signals until the cut-off frequency is reached. The reactance of the capacitor will reduce, and it will now act like a short circuit, allowing input signal to pass directly to the output. Now we are on PSpice, where I will show you the simulation. This is the circuit I've shown you earlier. So before we run the simulation, we have to create a simulation profile. I'm using a C-sweep analysis type. My start frequency is 10 Hz, ending at 10 kHz. Points per decade is 10. Okay. Now let's run the simulation. Now I'm going to add the trace Vout. This is our response curve. Now we need to find the cutoff frequency to determine which is the pass band. Earlier we've calculated that the cutoff frequency is 318 Hz. Now I'm going to find the cutoff frequency. Okay, so as you can see here, 317.9. This is closest to the cutoff frequency. That means that this area, the right side of the cutoff frequency, is the pass band, and the left side of the cutoff frequency is the stop band. The frequencies that will be passed are the ones on the right. Okay, that's all from me. Thank you.
Hello everyone, my name is Farizan and today I am going to talk about band pass filter
and band stop filter. Hello.
You see, the concept of band pass filter works like this. It only allows a certain frequency range to pass through it while it attenuates any other range outside of it. So as explained by my fellow friends just now, Erda and Sam, I think I put their face around here somewhere. Yeah, so they explained about low pass and high pass filter. You see, the creation of band pass filter is through the addition of low pass and high pass filter merged together. The circuit here is also here again, and then circuit over here. See this? See, this is the low pass and then this is the high pass. So we are going to use the capacitor circuit. Again, capacitor circuit, actually we start with the low pass filter first and then we continue with the high pass filter. And next, if we use inductor circuit, resistor inductor circuit, we start with a high pass filter and then proceed with a low pass filter. Now let me explain you the analogy of band pass filter using carom board. Now let's take this black carom ball as the frequency that we want and this white ball as the frequency that we want to eliminate. Now band pass filter will eliminate all of this frequency and tone it down while leaving the frequency that we desire at the top. In short, that is how band pass filter works, where we take the low pass and the high pass and conversion in the middle of all. Then we will obtain the frequency that we desire in the
Is it my turn yet?
Shut up you! In the first start.
The video shows the simulation for band pass filter using resistor capacitor circuit. As you can see from the graph shown, the peak value are the frequency that we wanted and the other frequencies have been toned down.
The application of band pass filters are mainly used on transmitters and receivers. In transmitters, it limits the bandwidth of the output so that we doesn't interfere with the frequency or other signals. And then in a receiver, it only captures a frequency that we desire and eliminates all other frequencies. Band pass filters can also help in astronomy, where it allows the light to travel only at a certain spectrum. It can help in finding the stars at the main sequence, identifying the redshift shift, and many other applications.
Yay! It's finally my turn to talk. Now I'm going to talk about band stop. band stop. Band stop has many names: band reject, band elimination, and notch filter. Band stop is technically the opposite of band pass, which is explained by Tim. Band stop is a filter that passes most frequency through it, but attenuates a specific range of frequency to a very low level. Band stop is technically a combination of a low pass filter and a high pass filter, but this time it's connected in parallel. This is an example of a band stop filter. This is the combination of a low pass filter and a high pass filter. This circuit is called a twin T circuit. The combination of this filter is 3 resistors and 3 capacitors. The notch frequency is equal to 1 over 4 pi R3 and C3. The notch frequency is the maximum frequency where the signal attenuates to the lowest level. Next is the notch filter. This is the simplest way a band stop circuit can be made into. Now I'm going to explain to you the concept of a band stop filter using a snooker, not like him, using tarot. You see this 11 volts? This represents signals. Band stop filters will attenuate one of the signals to a very low level. For instance, we will choose volt number 6. Oh, I missed.
How the hell did you miss yet? Are you blind or are you just dumb?
That's how a band stop works.
Okay, here we have a twin T circuit. The circuit has 3 resistors and 3 capacitors. We have a power source which has 45 Hz. And now let us begin the simulation. From the calculation we have obtained that the notch frequency is 60 Hz. So here's the output 5 volt and the output here where it keep on decreasing as it draws near to 60 Hz. And at 60 Hz the frequency will drop from a very low level around 3.5 millivolts, and as it gets further away from the notch frequency, it keeps on decreasing and goes back to the normal level. And that is how band stop filter works.
Now I'm going to explain about the application of a band stop filter. One of its applications is anti-hum filter. Some countries use a 60 Hz power line. This 60 Hz power line will filter out between 59 Hz, 60 Hz, and 61 Hz. Let me check my screen. Oh God. This means all the frequency will pass through the power line, but except for 59, 60, and 61. This means the main hum are filter. Because main hums, if you want to know, is, for example, you have a speaker and you have a power line of 60 Hz. When the power line is exactly at 60 Hz, you will show a sound like and I'm sure you don't like this sound, right? And this band stop filter will stop the 60 Hz current passing through the speaker, and eventually the sound doesn't come out to the speaker. Although higher frequency signal does pass through the power line, but that's it's not very frequent.